Hello everybody, and welcome to the second part of section 12.1, where we will briefly finish up the graphing in 3-space section, introduction to that section. So here's where we left off. We get a cylinder when we have this unit circle equation from 2-space. Now let me just move on to a sort of compound condition here. So you can always ask, hey, what points satisfy this and also this? What points satisfy the fact that the sum of the squares of the x and y, right, give you 1, and also the z-coordinate is 3. So you can think about what that looks like, but here, right, there really was no restriction on z, which is how we got this infinite tube up and down, this infinite cylinder. But now, though, there definitely is a restriction on z, right? So many of these points here don't work anymore. So like here at z equals 0, that doesn't work. Any negative z, anything beneath the xy plane doesn't work, etc. So what does work, though, is just this circle, right? The z equals 3 circle. So you take a tiny little slice off of that cylinder. So just to show you that sort of in action here, right? Here's that cylinder, and now if you also ask it to graph z equals 3, right, that plane slices that cylinder right there as z equals 3, and that intersection of the two curves is what you get. So it's sort of hard to get it in a way that's nice to look at here, but anyway. So you can always do sort of compound conditions and think about, oh, what does the graph of that look like? Finally here, y equals x. This is a very familiar equation from calc 1, calc 2, right? If you graph this in 3-space, then as you might imagine, you don't just get that y equals x line anymore. There's no restriction on z. So you're going to have things of infinite height here, and you end up with a picture like this. Here's that y equals x line in the xy plane. I'm not sure why this picture doesn't extend it all the way over to the left, but anyway, here's your y equals x line, and then you give it some height, so it becomes a sheet now, because there's no restriction on z. So if you think about a point like 113, 114, 115, 116, right? All those points are on the graph of that thing, which is how you get that infinite height. Okay, so that's a just sort of brief introduction to graphing here in 3-space. Okay, so let's finish by talking about spheres. Let's do something concrete in 3-space. These are all just sort of toy examples, and many of them, right, don't really involve x, y, and z. I mean, this was the only one that involved x, y, and z, and it was like a compound condition here, right? So let's actually look at equations that involve x, y, and z all non-trivially. Before we do that, though, with spheres, let me just give you the distance formula in 3-space. If you recall the distance formula in 2-space, this should look completely familiar to you. Just sort of cover up this part, right? The distance between x1, y1, x2, y2 in 2-space is take the difference of the x coordinates and square, add difference of y coordinates square, and square root that whole thing. Okay, so if you remember the distance formula in 2-space, this should not come as a shock to you that this is the distance formula in 3-space. Okay, so given that, the sphere with radius r and center c, where the center is thought of as HKL, it's the set of points in 3-space, all of whose distance from c is r. Okay, so all I'm saying is, right, you have a fixed center in mind. You then pluck out of 3-space, you graph all the points that are a distance r from that center. So distance 2, distance 3, whatever, right? As you increase that radius, you make the thing bigger. So this is actually the definition of a circle also. Replace sphere with circle. It's just circles live in 2-space. So you'd have to get rid of this L coordinate, just HK. Okay, so given the distance formula from before, if x, y, z, this arbitrary point, is going to be on that sphere, its distance from C to itself must be r. So x minus the sphere's x coordinate must squared must go there, etc. must all equal the distance. If you square both sides, you get this. Okay, this is the standard form of an equation for a sphere in 3-space. So to write down an equation of a sphere, if you know its center and you know its radius, you can just plop those numbers in there, and there's your equation of a sphere. And again, if you recall how circles work in 2 dimensions, this should not surprise you. The circle with center HK, right, I have to throw out the L because I'm in 2-space, It's just all of this, but delete the z part, right? That's the equation of a circle in 2 space. Okay, so here's the kind of question you might see in your homework. This equation sitting here does represent a sphere. I'm telling you that. I want you to then tell me about the sphere. What are its center and what are its radius? Or what is its center, what is its radius, I guess. Anyway, so of course the problem here, the thing for you to do, is notice that this equation looks nothing really like this equation, right? But if it did, if you had that equation written like this, you could just read off the coordinates of the center and the radius. So let me just do a little bit of work for you here. So notice this equation from before, this standard form, there's just a number on the right-hand side, and the x, y's, and z's are all grouped together. So like terms are all grouped together on the left-hand side. So let me just do that step. X squared plus 4x, y squared minus 6y, etc. And then what's left on the other side is just this negative 6, right? That 6 wasn't attached to an x, y, or z, so I throw them over on the other side. And now, to get an equation that looks like this, you have to complete the square. If you don't remember how to complete the square, I would Google it, or you can ask me later. But suffice it to say, when you complete the square, you end up adding a 4 to the x's, a 9 to the y's, a 1 to the z, and of course, if you had a 4, 9, and 1 over on the left, you have to add them on the right to keep things in balance. And the reason you did that, right, the reason that completing the square is nice is it lets you write things as a square. X plus 2 squared, y minus 3 squared, z plus 1 squared. And what's left on the other side is an 8. So from that, you can tell me the center is, just flip the signs on these numbers, so negative 2, a positive 3, negative 1. That's the center of the sphere, and the radius is root 8. Okay, so there's an example. So quickly here to end, here's just something you might see. Here's a compound condition, but just to let you think about what more complicated shapes might look like in 3 space. Here's an inequality, a couple of inequalities. 1 is less than or equal to x squared plus y squared plus z squared, which must itself be less than or equal to 4. Oh, and also z can be at most 0. So if you think about the second condition, it's saying that whatever you're going to draw here must live under the xy plane, right? The heights must be negative, or the heights must be 0. So you're below the xy plane, or you're on the xy plane. Notice just this little bit here. That's a sphere centered at the origin, right? Because there's like an x minus 0, y minus 0, z minus 0. So this guy here is the sphere centered at the origin. And what I'm saying is, take that sphere and let it start with radius 1 and end with radius 2. Got to be a little careful, right? This is like an r squared over here, r squared right there. So square root of 1 is 1, square root of 4 is 2 though, right? So anyway, what I'm saying here is like, look, take a sphere centered at the origin and let it range from radius 1, to radius 2, and only pluck off the stuff underneath the xy plane. And if you do that, you get this bowl-shaped thing, right? Radius 1 to radius 2 under the xy plane. Okay, so hopefully this has been informative and useful to you. Again, I realize this is suboptimal. It would be nice to look at your faces in class to see what makes sense and what doesn't. Please send questions via email or come to class on Monday with questions, and I will see you on Monday.